Viewers, welcome to my channel and thank you for watching the videos. In this video, question 6C of 1994 UPSC CSE Maths Optional Paper 2 Complex Analysis by means of contour integration, evaluate this integral. So first we have to think about contour. We will take semi-circular figure which is 0 to infinity, plus side is being taken. So fz is log z upon z square plus 1. So the whole contour has been divided into four parts, that is minus r2 small minus r, then gamma, that is minus r2r, then r2 capital R. This is basically x-axis we are taking, and r is very large which is tending to infinity. Then in this direction along semicircular arc tau, that is r2 minus r, and this is 0 which is branch point, and due to multiple valued function log z we have eliminated this, avoided this point. So this is the contour. Now the four parts we are having for calculating this whole integral. So addition of all those four will be, now z square plus 1 is equal to 0, so z square is I square, so z is equal to plus minus I are the poles. So z is equal to I will be the pole which lies in this contour, and minus I won't lie. So this is the point where z is equal to I. Now at pole we can find out residue, and residue will be limit z tends to I, z minus I log z whole square upon z minus I into z plus I. So this becomes log I, because it is base E, so we can say ln z, and when z is I, ln I whole square upon 2I. It is log base E, so we can say ln z whole square upon z minus I into z plus I, which is equal to ln I, because z is equal to I whole square upon 2I. So this is equal to pi I upon 2 whole square upon 2I, and which is equal to minus pi square upon 8I. So residue theorem says that integral closed integral fz dz will be equal to 2 pi I into minus pi square upon 8I, which is minus pi square upon 4. So now we take all the four parts and we will keep it equal to minus pi square by 4, which is the value at pole, residue value, which is the residue at the pole. First we will show that the integral over curved lines, that is gamma and tau, will be 0, and rest 2 we will calculate, and that we will keep equal to residue at the pole. So first we take tau, and on tau it is z is equal to capital R e to the power I theta, and denominator is z square plus 1. This will be greater than equal to, if we are taking mod, so mod z square minus 1. This is from the inequality, and mod z we are taking very large, so r square minus 1. So mod of integral tau fz dz is less than equal to 0 to pi, because semicircle is there, so angle will be 0 to pi for d theta, for theta, and log z we can write down log r e to the power I theta whole square upon r square minus 1, and dz is equal to I r e to the power I theta d theta mod of this. This will be less than equal to, we will take the mod inside, and mod inside gives log r plus I theta, that is log e I theta is I theta, and whole square of this. Mod of I and mod of e to the power I theta is 1, so r d theta, which is equal to, when we take r and we take r upon r square minus 1 as common, so 0 to pi, Now open the mod, so log r square plus I square theta square, and mod of that gives theta square d theta. And this is basically when we integrate it pi, because we are integrating with respect to theta, so log r will be constant, so log r square into pi plus pi cube by 3. Now when r tends to infinity, this whole term becomes 0 because r square minus 1 is in denominator, and this integral is 0. Similarly, we can see for gamma, there we are having z is equal to small r e to the power I theta, and mod of z square plus 1, only thing we are breaking or taking it in another manner, is greater than equal to 1 minus mod z square, which is 1 minus r square. Thus we can write down that mod of fz dz, mod of integral fz dz over gamma is less than equal to, now limit is here pi to 0, because gamma is direction is from minus r, so pi to 0 log r square plus theta square, as we did earlier, upon 1 minus r square r d theta. So this becomes r upon 1 minus r square pi log r whole square plus pi cube by 3, and when r tends to 0 here from right side, this becomes 0. In this r was tending to infinity. We have seen that fz has, so both are 0. Now we take rest in the upper two integrals. Z is equal to I lies inside the contour at z is equal to I. So residue at the pole is minus pi square upon 8i, which is equal to pi square I upon 8. So we have seen that two integrals are 0, the integrals over curve line, and here we have remaining two integrals which will be equal to 2 pi I into residue at z is equal to I. Now the remaining two integrals are r tends to infinity, r tends to 0, the first part from small r to capital R, this is on CD, where z is equal to x means real x's are there, dx plus capital R to small r, here it is on AB, where z is equal to x e to the power I pi. So dx e to the power I pi is dz. So dz is equal to e to the power I pi dx. So remaining two were 0, so this is the expression now. We substitute value z is equal to x and z is equal to x e to the power I pi in the integrals. So we reverse the limits. So minus infinity, that is capital R to small r 0, log x e to the power I pi whole square upon 1 plus x square e to the power 2 pi I dx, plus small r to capital R 0 to infinity log x, this is on real axis, log x whole square 1 plus x square dx, which is equal to minus pi cube upon 4. And now we take the numerator of this, log x e to the power I pi whole square is log x plus log e I pi whole square, that can be written as log x whole square plus I square pi square, which is minus pi square, plus 2 I pi log x. And this is basically twice 0 to infinity log x whole square upon 1 plus x square dx minus pi square dx upon 1 plus x square plus 2 pi I log x upon 1 plus x square dx over limit 0 to infinity. It is equal to minus pi cube upon 4. This 2 is due to 1 from here, and another from here. Now equating real parts and noting that 0 to infinity dx upon 1 plus x square is tan inverse x 0 to infinity, which is pi by 2. So here we have price of 0 to infinity log x whole square upon 1 plus x square dx is, this is pi square into pi by 2 is pi cube by 2 minus pi cube upon 4, which is on right hand side, and 2 pi I 0 to infinity log x 1 plus x square dx is imaginary part, so we will leave this. And here we can write from here that real part is equal to pi cube by 8, and equating imaginary parts we get 0 to infinity log x upon 1